Hello and welcome to our capstone project. My name is Ethan Reeds and I worked on a team with Fahad Awan and Donato Cortesia on a application called Top N Music Genre Classifier. Genre classification is not an easy problem. If you were to ask a group of people to listen to Bjork's music and classify what genre that is, there's bound to be some disagreement under what categories that fall under. So our genre classification app applies deep learning. We utilize a convolutional neural network and we attempt to answer questions like this.
At a high level, our application is made up of microservices: the audio processor, the ETL pipeline, the neural network, and the prediction API. We also have a front end for end user interaction. The audio processor is a core utility of our application. It converts sound files into images as spectrograms, as pictured here in my IDE. The extract, transform, load, or ETL pipeline service processes sound files using the audio processor and loads them into our SQL database to be consumed later by our neural network service. Here is an example of the ETL service in action. The neural network service trains a convolutional neural network using TensorFlow and Keras with the data from the SQL database that the ETL service loaded. The aim of the neural network is to create an accurate machine learning model which can predict what genre of music corresponds to each spectrogram. The front end is where the end user interacts with our application by uploading their sound clip and receiving a genre prediction. The front end communicates with the prediction API on the back end. The end user sound clip is run through the audio processor, followed by the model the neural network produced. Genre predictions are given, which are then displayed on the page. Hello, this is Fahad. As part of the development process, these are a couple of things that I worked on. First is a continuous integration pipeline that I set up using GitHub Actions. Every time a developer pushes code to our repository, a series of automated tests to run. Also, caching is implemented in order to speed up the installation of our heavy machine learning dependencies. Another CI tool I used was pre-commit hooks. These opinionated tools were installed in our repo so that my team wouldn't have to spend time deciding on subjective styling and spend more time developing. My main part of the project was working extensively on the audio processor utility. The audio processor consumes audio clips and produces spectrograms using NumPy and Librosa, like the one pictured here. The spectrogram is a visual representation of the spectrum of frequencies of a signal as it varies with time. The audio processor utility is a critical part of our project and is used by both the ETL service and prediction API. I also implemented multi-threading to speed up processing audio clips. The entire team worked on optimizing our neural networks model, but one contribution I made was increasing the accuracy by adding max pooling and normalization layers. The addition of these layers allows our model to have better generalization capabilities when building off our dataset. Finally, I collaborate often with teammates to solve the problems and challenges we face as a team. Machine learning is very complicated. I learned a lot about audio feature extraction, CNNs, and building CI pipelines.
I primarily worked on the project architecture, normalizing input, improving the user experience, database models, and implementing an endpoint for predictions. I wrote front-end components in React to make it easier to provide user feedback, as you can see here on the bottom right, and I used a Python library called Typer to implement a command line interface for our model generator, as it handles argument parsing and provides help text. I also added an input layer to our model that resizes images using TensorFlow, the machine learning library we use for the project. This solved a problem where tiny variations in audio length would crash our server. I wrote database models using SQL Alchemy, and while this made patching our database for testing more difficult, it allowed us to write database calls without relying on any dialect-specific statements. I implemented a predict genres endpoint using FastAPI, which is an asynchronous Python web framework built to minimize overhead. The benefit of using FastAPI is it generates documentation from the response models you've already defined in your code, as you can see here on the right. And finally, I Dockerized our application and deployed it to Heroku. This came with some challenges like having to refactor code to accept Heroku's environment variables, but overall, Docker is something I would highly recommend. Docker images work similarly to virtual machines, so they guarantee a consistent environment and they made deployment seamless.
So I worked on several parts of our application, first being the web front end. So here the user uploads a sound file and we first validate that that file is of the correct format and is at least 30 seconds in length. So this occurs in the web browser before the file is actually sent over to our backend prediction API. I also worked on that post request for our prediction API, which takes in the audio file, converts the audio file into a spectrogram image, and then feeds that image into the neural network, and finally returns the genre prediction results back to the user on the web front end. Before our neural network is trained, we depend on this ETL service. So here I worked on processing the directory full of WAV files. As they're being processed, they're moved into a new directory. Those WAV files are converted into images and stored into our database. The last thing I worked on is the optimization of our convolutional neural network. Several experiments were performed, varying the number of filters and kernel sizes used in the different layers.
Overall, our project was a success. We constructed a minimum viable product that applies deep learning on spectrogram images to classify music by genre. But as always, there's plenty of room for future improvement. Our model could be made more accurate with additional data, and supplying more fine-tuned genre labels and the ability to classify a clip into multiple genres would make it more useful. In addition, we hope to add support for pasted links to clips and for user feedback that would help us continue improving our model. Thanks for listening.